And this is the second in our lesson videos for today. And it's going to be a short PowerPoint that's going to give us more information about how to solve related rates problems. Now, I hope you watch the first one first, because that's the introductory one, because that's the video that kind of tells us what related rates problems are supposed to be and kind of introduces, what kind of problems you're going to be solving that are called related rates problems, and gives you some vocabulary about how to talk about related rates problems and introduces them a little bit. Okay, so here, now we're going to go ahead and we're going to talk about go into related rates a little more in a little more detail. Okay, so now, as you can see here, it says the derivative dy dx of a function y equals f of x is its instantaneous rate of change with respect to the variable x. And remember, in related rates problems, we're not solving for static quantities, we're solving for rates of change. The rate at which quantities that we're interested in are increasing or decreasing in relation to some other rate in that problem. When a function describes either position or distance, its rate of change is interpreted as a velocity. And then by velocity, we mean not only a magnitude like speed, but also a direction. In general, a time rate of change answers the question, how fast is a quantity changing with respect to time? For example, if V is the volume that is changing in time, then dV dt is the rate or how fast the volume is changing with respect to time. So for example, how fast the volume of the snowball was decreasing, say in cubic centimeters per second or something, as it sat on the counter melting. Okay? Or in the case of the rocket going up, as the rocket goes up, one rate in that problem is the rate at which the height above the ground is increasing, which is the same thing as the speed of the rocket, but also related to that was the rate at which the observer's eyes are tracking upwards, say in degrees per second. How fast your eyes have to go up in order to keep your eyes on the rocket. Okay, and those two rates are related to each other. Okay, hence the name related rates. Okay, here's another scenario. If a person is walking towards a street lamp at a constant rate of 3 feet per second, then we know that 3 feet per second, that's the rate at which the distance is changing. The distance x that the person is from the street lamp, right? Okay, it's 3 feet per second. Now, in this case, since the distance is getting smaller, they're walking towards the lamp so that the distance is decreasing. So although that rate is 3, mathematically we call it a negative 3, because the x is a decreasing function, and so its slope and its derivative would be negative. So we call that negative 3 feet per second. If they're walking away from the lamp, the distance is increasing. The distance x, you understand, with respect to time, and so that's an increasing function, and so therefore the derivative, again, which is the velocity 3 feet per second, is increasing. Or rather, it's going to be positive. The 3 is not increasing, the x is increasing, but 3 is positive because it represents, which is the derivative, because it represents an increasing function. Okay, so now here are some guidelines for solving related rates problems. Okay, and there's 5 steps. And then they're really the same basic 5 steps that we have for solving any other kind of math word problem. They're just specifically adapted for solving related rates problems. The first one is we're going to draw a picture of the situation, and our related rate situations will almost always represent physical situations like volumes changing or distances changing or angles changing or something like that. Okay, so we'll make a sketch and we'll label it with all of the unknowns in the problem. Okay, then we're going to read the problem again, and we're going to identify all the quantities as find, when, and given. Now, what that means exactly, we'll see when we get to one of the problems specifically, but basically what we're doing there is we're specifying with variables or expressions all of the unknowns in the problem, including the one that we're trying to solve for. Then what we're going to do is this is going to start to sound familiar. We're going to write an equation that relates all of those quantities together. Step 3. And we did that a lot with the optimization problems, right? But then what's going to make this new is step 4 is we're going to take the derivative of that basic formula. That equation that we got in step 3, we're going to take the derivative of that, because it's that derivative version of the formula that's going to allow us to solve for the rates of change that we're interested in. Okay? And by the way, because we're going to have two different variables, at least two different functions that are both a function of time, not a function of each other, we're going to be using implicit differentiation in order to actually take the derivative. Okay? So among the things we're going to do on our homework here is I'm going to give you some problems to practice and to review the implicit differentiation. Okay? And then after completing step 4, we're going to take any known quantities, distances or times or something, and we're going to substitute them into the differentiated equation to solve for the derivative that we're interested in. Okay, and that's going to be an important point. We don't substitute into 3 because we're not interested in solving for static quantities. We're going to substitute into 4 because we're solving for the rates of change, for the derivatives. Okay, very good. So now, next slide is the first problem we're going to get at. Now, I'm not going to do that here on this video here because it's kind of awkward to write on the screen. I can kind of do it, but it doesn't look very nice. So I'm going to end this video right here. And then you're going to go to video number 3, in which I solve this problem and some other ones. Okay, very good. And we kind of get to the specifics of how we're going to solve a related rates problem. Okay, very good. Thank you.